Hi everyone, in this video we're going to talk about resonance. Resonance is a really important concept in organic chemistry because it determines the stability and reactivity of a lot of organic compounds. So let's remind ourselves what resonance is, how we can construct resonance structures, and what are the common structural scenarios where resonance would be important. Resonance arises when a molecule can be described by multiple Lewis structures, such as the case in this carbonate ion. But not a single one of these Lewis structures accurately represents what is actually happening in the carbonate ion. The real-life structure of a carbonate ion is actually an average of all three of these resonance structures, and all three of the carbon-oxygen bonds are identical. Remember, when you draw the various resonance structures, they are not converting into one another, but rather mentally average all of the resonance structures in your head. To convert between these different resonance structures, we have to move the electrons using curved arrows. And in doing so, we have to make sure that we never exceed the octet. Now let's go over the 3 commandments of constructing resonance structures. The first commandment says, do not break single bonds. The second commandment says, only the electrons move when showing resonance structures. Atoms do not move. And the third commandment says, do not exceed an octet. Now let's review the steps for writing resonance structures. First is find the electrons to move. And again, only the double bonds or lone pairs can move when you're drawing different resonance structures. Then find a place for those electrons to go to. And these electrons from double bonds or lone pairs can go into a valence vacancy, meaning a cation, into a lone pair, or into a double bond. Then draw the curved arrow starting from where the electrons are and pointing it to where they are going. And lastly, but most importantly, make sure that the octet is not exceeded when you've done the move. In this example of the acetate ion, we can move one of the lone pairs on this oxygen and make it into a double bond. But when we do that, notice that the octet on the central carbon would be exceeded. So then we have to move the double bond to become a lone pair to ensure that the octet is not exceeded on any atom. Now let's take these concepts that we just learned and apply them to 5 different scenarios where resonance is involved. The first is a pattern of 3 atoms, the first of which have a double bond between them, and the third has a lone pair. Second scenario is a cation 1 bond away from a double bond. Third scenario is a cation adjacent to an atom with a lone pair. Fourth scenario is alternating single and double bonds. And the last scenario is double bonds with one atom more electronegative than the other. Here's an example of the first scenario. The ABC pattern where C has a lone pair and A and B have a double bond. This is similar to the carbonate ion that we saw earlier. In this kind of a scenario, the resonance structure is derived by moving one of the lone pairs to construct a double bond, and simultaneously moving this double bond to become a lone pair, which results in the following structure. Notice that the formal negative charge migrated to this carbon. In our second resonance scenario, we have a cation that is 1 bond away from a double bond. We would start building the resonance structure by moving the double bond electrons to fill the vacancy where the positive charge is. In the resulting structure, the carbon's valency has been filled by the double bond, and the positive charge now resides on the oxygen. The third resonance scenario is a cation adjacent to an atom with a lone pair. In this scenario, we also want to fill the valence of the atom with the positive charge, and we do that by moving the lone pair electrons of the atom next to it. This results in a structure where there is now a double bond between the oxygen and the carbon, and the positive charge is now on the atom that donated the lone pair. The fourth resonance scenario arises out of alternating single and double bonds. To draw the resonance structures, we take the double bonds and we move them over to the area where there's currently a single bond. And remember, we have to not exceed the octet when we do that, so we have to simultaneously move over the nearby double bond. And then to ensure that this carbon's octet is not exceeded, we move the double bond that is attached to it as well. This gives us a structure where all of the double bonds have been shifted. And this is actually called aromaticity. In case of the linear alternated single double bonds, we start drawing the resonance structures in the same way by moving the double bond electrons over to the adjacent bond. However, when we get to this last double bond, notice that we cannot move it over here because then we're going to really exceed the octet on this last carbon, and there's no way for those hydrogens to get removed. So instead, we're going to put this last double bond to become a lone pair on this carbon. And notice that in the resulting structure, we created a positive charge on the carbon from which we removed the initial pair of electrons, and we created a negative charge into which we put the electrons from our last double bond that we moved. But not all resonance structures contribute equally to the resonance hybrid. Some structures are better than others and will represent the resonance hybrid more. And typically, the lower energy resonance structures will contribute more to the resonance hybrid. For example, in the case of acetic acid, we recognize that we have resonance scenario number 5, a double bond with an atom that is more electronegative than the other atom. So we can construct a resonance structure by moving over this double bond to become a lone pair, resulting in a negatively charged oxygen and a positively charged carbon. And once we've done that, notice that we've now created resonance scenario number 3, where there's an atom with a lone pair next to a cation. So we can create another resonance structure by moving these electrons of the lone pair of the oxygen to create a double bond with the carbon. So even though these last two structures are both not very large contributors to the overall resonance hybrid, the structure on the far right is probably worse than the one in the middle because the charges are separated further, making the structure less stable. Now let's take a look at some examples and see if we can recognize the resonance scenarios. In this compound, notice that we have resonance scenario number 5, a double or a triple bond where one of the atoms is more electronegative than the other. So we can move over a pair of electrons from the triple bond onto the more electronegative atom, which is the nitrogen in this case. And notice that we again have charge separation, where the negative charge is now on the nitrogen and the positive charge is on the carbon. And in this resonance structure, we recognize resonance scenario number 3, where we have a lone pair next to a cation. So we can write another resonance structure by moving one of the lone pairs to become a double bond with the carbon. In our final resonance structure, we have the negative charge on the nitrogen and a positive charge on the oxygen. So out of all of these resonance structures, I would say that the least stable one is probably this one, because the positive and the negative charge are separated very far from one another. And this last resonance structure likely does not contribute a whole lot to the overall resonance hybrid. Let's take a look at another example. In this case, we recognize again that we have resonance scenario number 5, where there's a double bond in which one of the atoms is more electronegative than the other. But we also have resonance scenario number 4, where we have alternating single and double bonds. So we would start drawing our first resonance structure by moving the double bond electrons to become a lone pair on the oxygen. And we can simultaneously move the pair of electrons from one of the double bonds in the ring to become an adjacent double bond here. In the resulting structure, we have charge separation with the negative charge residing on the oxygen and the positive charge residing on the carbon. Another option is to start moving the electrons in this alternating single double bond chain toward the carbon. So we could take this double bond between the carbon and the oxygen and move it over here. In doing so, we ruined the octet for this carbon here, so we would have to take the double bond between these two carbons and move it over onto the carbon here. When we do that, we leave the oxygen with a positive charge, and we create a lone pair and a negative charge on the carbon. So given what we know about electronegativities, the first resonance scenario is more likely because the more electronegative atom has the negative charge. So out of all of these resonance structures, this structure here likely contributes the least to our overall resonance hybrid of this molecule. Now go ahead and try this last example on your own, and I will provide the answers in the post-lecture notes. Hope you found this video to be informative, and let me know if you have any questions. See ya!